You hear this word all the time, right? Pure. We're always looking for things that are pure. But have you ever really stopped to think about what that word means? Well, in this explainer, we're going to discover that from a scientist's perspective, the world around us is not quite what it seems.
I mean, you see it plastered all over packaging, don't you? Pure milk, pure salt. And for most of us, that just means, there's no junk added. But for a scientist, that label is almost always wrong.
And here's why. In science, the word pure has a really strict definition. A pure substance is made of only one single type of particle. So that milk you might have had this morning, it's actually a mix of water, fat, proteins, a whole bunch of stuff. So, scientifically speaking, it's not pure at all. And once you get this one little difference, you start to see the entire world like a chemist.
All right, so here's our roadmap. First, we'll nail down the difference between pure substances and mixtures. Then, we'll dive into solutions, suspensions, and colloids. After that, we'll break down elements and compounds, and we'll wrap it all up with physical versus chemical changes. Let's get into it.
Okay, let's start with that first big dividing line that scientists use to classify basically everything. Is it a pure substance or is it a mixture?
So, here's the deal. A pure substance, like a grain of sugar or plain old salt, is made of just one thing. It's chemically the same all the way through. You can't just filter it or boil it to get simpler ingredients. But a mixture, like seawater, that's just a bunch of different things hanging out in the same place. You can easily separate the salt from the water just by letting the water evaporate. That's how you know it's a mixture.
But here's the thing. Not all mixtures look the same. Some, like salt water, are called homogeneous. The salt dissolves so perfectly and evenly that you can't see the individual bits. It all looks like one thing. Others, like oil and water, are heterogeneous. You can shake them up all you want, but you're always going to see those separate, distinct layers.
Okay, so let's zoom in a little closer on this world of mixtures. Turns out there are three main types we really need to know: solutions, suspensions, and these really interesting ones that are kind of in between. They're called colloids.
So a solution is your classic homogeneous mixture. You've got one substance, called the solute, that gets dissolved into another substance, the solvent. The key here is that the particles of the solute are incredibly tiny, so small that they spread out perfectly, they never settle to the bottom, and a beam of light just passes right through.
Now, obviously, solutions can be weak or strong. Think about weak coffee versus strong coffee, right? That strength is what scientists call concentration. And they don't just eyeball it, they have precise formulas to calculate it, using the mass or the volume of the solute and the solution to get an exact percentage. For instance, let's say you took 40 grams of salt and dissolved it in 320 grams of water. You just plug those numbers into that first formula, the mass by mass percentage. You run the calculation, and bam, you've officially created a solution with a concentration of 11.1%.
All right, now for the other two. A suspension is a heterogeneous mixture where the particles are big enough to see, and they'll eventually settle out if you leave it alone. The classic example is muddy water. And then you have the colloid. These are the tricky ones. A colloid often looks homogeneous, like milk does, but it's actually heterogeneous. Its particles are bigger than in a solution, but still too small to see, and they never settle out, which makes them super stable.
So, here's a great way to see them all side by side. Check out the differences in particle size and stability. But my favorite one is that last property, the Tyndall effect. It sounds fancy, but it's just a term for scattering light. And you've seen this a million times. It's why you can see sunbeams cutting through a dusty room, or your car's headlights in the fog. That dust and that fog, they're perfect examples of colloids.
Okay, that's a good look at mixtures. Let's jump back across that divide and focus on the other category, pure substances. What are these things actually made of?
Well, pure substances come in two main flavors. First, you have elements, like iron or oxygen. These are like the Legos of the universe, the fundamental building blocks that you can't break down into anything simpler using a chemical reaction. But when you chemically combine two or more of those elements together in a fixed recipe, you get a compound, like H2O, water.
Let's actually see this in action. Imagine we take some iron filings and some yellow sulfur powder, and we just, stir them together in a bowl. We've just made a mixture. Now, if you bring a magnet close to that mixture, it'll pull the iron filings right out. Why? Because the iron is still iron, and the sulfur is still sulfur. Nothing has chemically changed. They're just physically mixed.
Okay, but now let's take that same exact mixture and apply some serious heat. A chemical reaction starts to happen. The iron and the sulfur atoms actually bond together and form a totally new substance, iron sulfide. It's this black, brittle solid, and if you bring a magnet near it, nothing happens. The iron has lost its magnetic property because it's not just iron anymore. It's part of a brand new compound.
So the takeaway here is huge. Making a mixture is just a physical jumble. The original ingredients keep their identities. But making a compound is a chemical reaction. It creates a brand new substance with a fixed recipe and completely different properties from the stuff you started with.
And that whole experiment with the iron and sulfur, it leads us perfectly into our final topic, the two fundamental ways that matter can change.
Okay, so first up is a physical change. This just alters the form of a substance, not what it's made of. Melting an ice cube is a perfect example. It turns from solid to liquid, but it's still H2O. And you can easily freeze it back into ice. But a chemical change or a reaction makes a completely new substance. When you burn a piece of paper, you get ash and gas. You can't turn that ash back into paper. That's a chemical change. It's irreversible.
So let's do a quick recap. We've learned that all matter is either a pure substance, which is an element or a compound, or it's a mixture. We know those mixtures can be smooth solutions, chunky suspensions, or those tricky, light-scattering colloids. And we know that matter is always transforming, either by changing its physical form or by changing its actual chemical identity.
And that's our deep dive. But here's one final thought for you to take away. Just look around you, right now. The air you're breathing, the desk you're at, the drink on your table. With everything you've just learned, can you start to classify the world in a completely new way?